Ramadan, and today we're going to be explaining the sliding filament theory and how it shortens, lengthens muscles, and how it is affected by rigor mortis. So first, a neurological impulse is sent to the neuromuscular junction right here, which prompts the sarcoplasmic reticulum to release calcium ions. Alright, so once the calcium is released, it binds to the troponin on the actin, which changes the shape of the trypomyosin to reveal the active site of the actin. Then the myosin heads of the myosin can bind to the active site of the actin. Once a cross bridge is formed between the myosin head and the active site of the actin, a power stroke can occur to move the actin and shorten the muscle. Once the power stroke has occurred, ATP can bind to the myosin head, and it is used up to break the cross bridge between the myosin head and the active site of the actin. Once the ATP is used up, it provides enough energy for the myosin heads to attach again to the active site and do another power stroke. This occurs as many times as needed until the muscle is fully contracted and shortened. When it is time to lengthen the muscle, the calcium comes off of the troponin and returns back to the sarcoplasmic reticulum. This causes the trypomyosin to shift back and cover up the active site again of the actin, and then the actin goes all the way back to how it was in the beginning, and the muscle becomes relaxed. Rigor mortis, our body is not breathing, so we're not able to produce any new ATP. And without any ATP, we can't break the cross bridge between the myosin head and the actin binding site. So our muscles are basically stuck the way they were when we ran out of ATP and become stiff.